My previous thermo video reviewed the important vocabulary and concepts of thermochemistry. In this video, we'll look at the quantitative calculations of heat change associated with the various physical processes. Let's start by looking at the quantity of heat associated with changing the temperature of an object, but not yet changing the state of matter of the object. Recall from the previous video that different materials absorb heat at different rates. This is referred to as their specific heat capacity. If you added approximately 8,500 joules of heat to a 1 kilogram bar of gold and 1 kilogram of water, the temperature of the bar of gold would rise almost 70 degrees Celsius, while the temperature of the water would only go up 2 degrees Celsius. This is because water has a much higher specific heat than gold. The same amount of heat added to the same quantity of the two materials has a much smaller effect on the temperature of the water than the gold. The equation to use when added heat causes a change in temperature is Q equals mc delta T. Q stands for change in heat. This is usually measured in joules, but the calorie is another common unit for heat. M is mass, C is specific heat, and delta T is change in temperature. Change in temperature always means final temperature minus initial temperature of the object. Look at this question. The temperature of a 95.4 gram piece of copper increases from 25 to 48 degrees Celsius when the metal absorbs 849 joules of heat. The question asks, what is the specific heat of copper? We just saw that the equation to use is Q equals mc delta T. For which variable are we solving? We're solving for C, the specific heat. Let's substitute our other numbers in and solve. In the question, Q is given as 849 joules. The mass is 95.4 grams. C is what we're solving for. The final temperature was 48 degrees Celsius minus the initial temperature, 25. That's a difference of 23 degrees Celsius. So now solving for C, we get 0.387 joules per gram times degrees Celsius. Here's another question. In this one, it asks how much heat is required to raise the temperature of 250 grams of water 52 degrees Celsius. If you haven't already, memorize the specific heat of liquid water. It will not always be given to you, and you'll need it quite a lot. The specific heat of liquid water is 4.18 joules per gram times degrees Celsius. We're going to use the same equation, but this time we're solving for Q. The mass of the water is 250 grams. The specific heat that you have memorized is 4.18. And this question gives us the temperature change, not the final and initial values, but the change itself. So we substitute that in. When we solve for Q and round off to two significant figures, because of the temperature change, we get 54,000 joules. We can do more than just change the temperature of our object, though. We can add enough heat so that the object undergoes a change of state. This process can be viewed graphically as a heating curve. This is a graph of temperature versus time as heat is added at a constant rate. It shows the physical changes that are occurring at all times. We're watching the temperature as heat is being added at a constant rate over time. we are going to see that as heat is added, the temperature does not rise smoothly. Instead, the temperature rises, then plateaus for a time, then begins to rise again. While this is the heating curve specifically for water, most substances have a heating curve that looks like this shape, at least generally. The slopes of the lines might be different. The temperatures at which you get the horizontal lines would be different, but you have this rise, flatline, rise, flatline appearance in most heating curves. Let's look through the heating curve in detail. Initially, at time 0, we have solid ice. As we heat, the temperature increases. We are increasing the kinetic energy of the solid particles. When we reach 0 degrees Celsius, the temperature no longer changes, but we're still adding heat. What's happening at 0 degrees Celsius that's using that heat? The water is melting. The heat is being used to weaken the attractions between the particles. The temperature remains constant until the phase change is complete. Now we have liquid water. Now the added heat will again change the temperature of our sample until we get to 100 degrees Celsius. Then the temperature flatlines again. What's happening here at 100 degrees Celsius that is using the added heat? The water is vaporizing. Heat is being used to liberate the particles from the liquid state to the gaseous state. The temperature will not change until that process is complete. Once it is done, if we continue to add more heat to the sample, we can raise the temperature of the vapor even further. In 3 of these segments, temperature increases linearly. These segments represent the heating of a single state. The rate at which the temperature rises is based on the substance's specific heat in that state. In 2 of these segments, the temperature is constant as heat is added because the heat is producing a change of state. Anytime the added heat is used to raise the temperature of the object, you can use Q equals mc delta T to calculate the amount of heat absorbed. C is a constant for any substance for each state of matter. As I said before, you need to memorize the specific heat of liquid water, 4.18 joules per gram times degrees Celsius. The specific heats of solid and water vapor are different numbers. Depending on the textbook or the reference source that you use, they might be slightly different, but one possible value for the specific heat of solid is 2.1, and for steam, 1.99. Q equals mc delta T works fine when the temperature is changing. But this equation won't work to calculate the heat added for a phase change. The temperature change is 0, but we're definitely still adding heat. So we have to use a different equation to calculate the amount of heat associated with a phase change. That equation is Q equals N times delta H. N here means number of moles, because your delta H values, the heat change for that state, will be in kilojoules per mole. For melting, the delta H is called the heat of fusion. The term fusion is used for melting because if you heat several individual crystals of a solid, they will fuse into a continuous liquid upon melting. For boiling, delta H is the heat of vaporization. The heat of fusion for water is 6.02 kilojoules per mole, and the heat of vaporization is 40.7 kilojoules per mole. So there you see all of your constants for water. The only one you have to memorize is the specific heat of liquid water. All others will be given on quizzes or tests. Here's a typical question. How much heat is required to convert 55 grams of liquid water at 22 degrees Celsius to steam at 105 degrees Celsius? First, think about whether this is one calculation or a multi-step problem. How do you know that? Well, for one, this question is kind in its wording. It says liquid water to steam. But even without that verbal hint, the temperatures tell you. You have to understand that every segment of a heating curve represents a process that is unique from the other processes in some way. Raising the temperature of liquid water is different from boiling the water. Even one temperature change process is different from another because the two states have different specific heats. Visualize a heating curve for water. You should know in your head that water undergoes phase changes at 0 and 100 degrees Celsius. If the temperature range of a question passes through either of those temperatures, you have multiple segments to account for. You'll have to do multiple calculations to complete the question. In this question, we start at 22 degrees Celsius. That's low in the liquid water segment of the graph. We go to 105 degrees in the steam segment. That means we have to do a Q equals MC delta T calculation for raising the temperature of the liquid, then Q equals N delta H for the vaporization process, then another Q equals MC delta T for raising the steam's temperature. For raising the temperature of the water, we'll use Q equals MC delta T. The mass of the water is given as 55 grams. We need the specific heat of liquid water, 4.18. And for this change in temperature, we are going from 22 degrees Celsius to 100 degrees Celsius. That is the maximum temperature for liquid water. So that'll be 100 degrees minus 22. When we do that math, we get a heat change of 17,932.2 joules. At that point, we would have liquid water at 100 degrees Celsius. The next thing to do is to change the state of the water. For that, we need to do N times delta H, and that delta H will be the heat of vaporization. N stands for number of moles. So if we have 55 grams of water, we need to use the molar mass to convert that to moles before we can multiply by the heat of vaporization. The heat of vaporization is given in kilojoules per mole, so we have to do the conversion for grams to moles in this calculation. Multiplying all that together, we get a heat change of 124.251 kilojoules. We would now have steam at 100 degrees Celsius. We are asked to heat the steam to 105 degrees Celsius. So using Q equals, just kidding, MC delta T, we put in 55 grams. This time we need the specific heat of steam, which was given as 1.99. And we are heating from 100 to 105 degrees. So 105 minus 100. That gives us a heat change of 547.25 joules. For our final answer, we need to add these values together. But first, we have to deal with the fact that two of our values are in joules and one is in kilojoules. You need to convert. It doesn't matter which way you go, but one way or the other, you have to convert the values before you add them together. It's going to be a very big number if you choose to convert to joules. I usually convert these values to kilojoules. This first value then in kilojoules is 17.9322. And my third value is 0.54725. To get my total, I'm going to add them together. What will be the correct number of sig figs for my answer? That takes a little bit of time to figure out. We need to look through each step in the process, look at the sig figs for each of my number of kilojoules, and then use the addition-subtraction rule. In this first step, when we did 100, which is the boiling point for water, we can consider that to have as many significant digits as necessary. So what really matters is we're doing a subtraction step where this value goes to the tenths. So my answer, 100 minus 22, 78.0 goes to the tenths digit. I have 3 sig figs there, and 3 sig figs, when you look back to the original value given in the question, 3 sig figs for my mass. So my number of kilojoules from the first step is significant to 3 digits. That 9 is the last significant digit here. For my second calculation, the only value that's not a conversion factor or a constant is my mass. The mass has 3 sig figs. So my second number of kilojoules would go to the ones digit. That would be the third significant figure. In my third calculation, the temperature 105 was given only as that, 105. So 105 minus 100 can only go to the ones place. That's only one significant digit. The kilojoules from this calculation only has one significant digit, so it's only the 0.5. Now, for my answer, I need to use the addition and subtraction rule. I have one value that goes to the tenths, another to the ones digit, another to the tenths. My answer goes to the ones digit. The correct answer here would be 143 kilojoules. Questions can also go in reverse. They can refer to the cooling process for a substance. On a cooling curve, temperature changes are always negative. If a sample is cooling, its final temperature is lower than its initial temperature. Final minus initial then would result in a negative number. Additionally, the delta H values are negative. However much heat would be added to vaporize a sample of water, the equivalent amount of heat would be released by that sample when condensing. So the heat of condensation is just the negative of the heat of vaporization. And the heat of solidification is the negative of the heat of fusion for the same reason. Also, notice, if you haven't before, that freezing and melting occur at the same temperature. The only difference between the processes is whether heat is being added to the solid or removed from the liquid. Boiling and condensing occur at the same temperature too.